This is our last part of limits algebraically. So we looked at different ways to evaluate when you're given a function, such as substitution, factoring and simplifying, multiplying by the conjugate. With piecewise, we want to look at both sides. We went through some examples and we saw what their matching graphs look like. We did an example of piecewise. And then in part 2, we looked at limits as x approached positive and negative infinity. And we used something called spit in the ocean. To eliminate the spit, just focus on the parts of the function that are growing the fastest. And we went through some examples. Today we're going to focus on some just review of rational functions from Algebra 2. So here are my first two examples. The limit as x approaches 1 from the right of this function. So if I do direct substitution, I get 1 over 0. That, of course, we can't divide by 0. It's undefined. And if you think about a rational function, this is just the graph of this function shifted to the right 1 unit. So we have a vertical asymptote right here at x equals 1. Our graph looks like this. Okay, that's just our parent function shifted to the right one. And this limit's asking us for the limit as x approaches 1 from the right. So we're going to be starting on this side from the right of 1. And remember, 1 is our vertical asymptote. Well, our graph, as we get closer to 1, our graph is going up forever. So we can say that the limit is equal to infinity. Now, I did say that for a limit to exist, it has to be a real number. And so in this case, we're going to say infinity or does not exist. In the next problem, it's asking about both sides. It's not side specific. There's no plus or minus side. And so this one is just does not exist because we can see the right-hand side is going up forever, the left-hand side is going down forever. In order for the limit to exist, it has to be the same value. And so that one just does not exist. On a multiple choice test, you might have an infinity or you might have a does not exist. You have to understand that that means the same thing. All right, so now some more or less common rational functions. When you have a squared term, such as this one in the denominator, that whether you square a negative or a positive value, it's always going to be a positive result. And so I can think about this is this function is shifted to the left 3, and so we have a vertical asymptote at negative 3. And because of that square, both ends of the graph are going to be going up. So the right-hand side and the left-hand side are going to be going up. And so we're not looking at one side, we're looking at both sides. The left-hand side of negative 3 and the right-hand side of negative 3, well, they're both approaching infinity or does not exist. Okay, in this next problem, I'm going to go ahead and rearrange the denominator. So I have negative x plus 5, and then I'm going to go ahead and factor out a negative. And so really what I'm looking at is the limit as x approaches 5 from the left of 1 over negative x minus 5. And so what this graph looks like is I've got a horizontal, horizontal shift to the right 5. I have a vertical asymptote at 5. But instead of usually being in quadrants like 1 and 3, the negative is going to cause it to reflect. And so it's going to look something like this. And so the limit as x approaches 5 from the left. From the left side as we approach 5, it's going up forever. And so that's going to be infinity or does not exist. All right, in the next problem, same situation. This time, though, we are squaring, and so both ends of the graph will be going up. So as x approaches 5, we can say positive infinity or does not exist. And in this last example, we're shifting it to the right 2, and we're reflecting. So This one's going to be something like this. Here's my vertical asymptote at 2. That's the horizontal shift to the right. And we're reflecting over the x-axis. So our graph is going to look something like this. Okay, so the limit as x approaches 2, we could say negative infinity or does not exist. Here's just some more examples using a graph. So if you want to pause the video and look at those, you can. But I did want to spend just a few more minutes just going over some Algebra 2 or some pre-calculus review of asymptotes with rational functions. Now remember, the horizontal asymptotes, those are determined by the degree of the numerator and the denominator. And so if the degrees are the same, it is the ratio of the leading coefficients. So in this case, that would be 1/2. The coefficient of x squared is 1, the coefficient of x squared in the denominator is 2, and so that's just y is 1/2. Now the vertical asymptotes, those are found as zeros of the denominator. So what we've got to do is factor this denominator and then solve those factors. I use our bottoms up factoring. And so you multiply the first and the last, that gives you -8. And we need two numbers that add to get -7. And so that's -8 times 1. Because we have a leading coefficient other than 1, we have to divide both of these terms. And if you can reduce. If you can't, the bottom number comes up. So here's the factored form of my denominator. If I solve each of those, I'm going to get x is 4 and x is -1/2. Those are my vertical asymptotes. All right, one last problem. Factor the denominator. Two numbers that multiply to get -24 and add to get 5 would be 8 and -3. My common factor, x minus 3, will cancel. And so this is just h of x is equal to 1 over x plus 8. This is just our parent function shifted to the left 8. And so I have a